All right, let's get going. New hat, new day. All right, so we're looking at using nuclear chemistry to determine age and amounts, initial or final amounts, because these things are how we actually practically use nuclear chemistry. So a little review. Half-life, we've got the idea of it being your 0.693 over K, K being your rate constant. You got your integrated rate law. This is the one that uses ln. When we think of this, you would almost always be using defined K. Right? K is helpful to find these other things. We used this before because these were concentrations of like gases and aqueous. Now these are amounts, which it says nuclei, like number of nuclei, but really these can be grams. They could be milligrams, micrograms. They could be any type of relationship. To where NT is the number of radioactive material at time t, and this is what you started with. Other arrangements that can be helpful could be something like this, to where you're separating and you're subtracting it. Radioactive dating is very similar to where they take the rate t over the rate naught, to where the rate naught is be able to predict how much time has passed. So the idea is that these can be used in order to determine this, and you can see that radioactive dating, every half-life, it's half as much. So it's kind of an exponential decay as we have through here. So when it's with carbon or other stuff, you essentially will always need to find K, or be given it. And then you're essentially finding out other components that are part of this. Now you need to find one of the variables. Sometimes percents are used. So either use the percents or the decimal equivalents. Make sure you kind of put those together. Get used to finding and using different arrangements of equations. Some of them make more sense than others. The idea is in using these, I like having the idea of this one at most times, because then a negative value of it divided by K is going to be equal to time. So that's how much time has passed. There's really good examples in the textbook. I think the ones that they put in there are really solid. And then doing a few with Pearson that are assigned help you kind of practice what they have for those to get in. I'm not going to go through examples here and probably just give you the same thing that you can see in the textbook. I wouldn't think that's a good use of your time. So this is like the regular one. Now, when it's dealing with uranium or lead, you have one other advantage here. Now, this is always looking at like a time scale. This is the T is equal to this divided by K. I use that quite a bit in my problems when I was from Pearson. This, though, has an additional part to it, because they tell you how much lead is found in the decayed model. And so if that's the case, you need to calculate how much of the original uranium was present. So you just convert it back to the uranium and add it to what was left over. So you have what was left over, and you need to know the original, and so the amount of lead is not the same mass. You need to convert the amount of lead into that original amount of uranium and add them together. Then you have that initial amount. You plug it in, you can find it out. So, I'm here to provide you any kind of help when you're doing these in class. Let me know how I can help. I'm here to help you. See you soon.